Perfect. Looks great. Take it away. Yair.
Okay. So thanks everybody for the opportunity to speak here. My name is Yair. I'm a postdoc at Oded Aronson's group at the Weizmann Institute, working with him and with Aviv Ophir. And I'm going to present AnalyticLC, which is an analytic tool for light curve modeling. It was designed for light curve modeling, but it does also other things. And the question under investigation here is how to invert a light curve into planetary parameters. The most direct way to do that is by performing a large number of n-body integrations, which is an accurate method, but sometimes it's computationally heavy. And therefore, many people have turned into analytic formulae for TTVs that enable fast inversion of transit times into planetary parameters. However, in some cases, if the planetary transit is extremely shallow, like in this example here, it's hard to constrain the individual transit times, and therefore you can't really get a lot of information from the transit timings. In such cases, it's desirable to use the entire light curve simultaneously and integrate over all of the light curve together. And there's another benefit for using the entire light curve and not just transit times, and that because you're using all of your information, including other types of transit variations, as in this nice example, where Mills and Fabrici detected transit duration variations in the system Kepler 108 that led to the inference of a high mutual inclination between the planets in this system. So what AnalyticLC aims to do is to balance between speed and accuracy. So in terms of speed, it does everything analytically, so it's faster than an n-body integration. And in terms of accuracy, by modeling the entire light curve and not only the transit timing variations, and it also incorporates three-dimensional orbital dynamics. So this is the flow of AnalyticLC, how it works. So we're solving Lagrange planetary equations that give us the variations in the orbital elements based on the disturbing function formalism that has been presented here before. And we get the variations in the orbital elements of all planets. You're seeing here the changes in the eccentricity as a function of time, but we do the same for all orbital elements. And these in turn are translated into individual transit properties, namely transit timing, impact parameter, duration, etc. And what you see here in panels B and C is a typical comparison of the analytic calculation with a full n-body integration that gives you the TTV. So you see there's a nice match between the analytic and the n-body integration in terms of TTV and impact parameter. And lastly, we compute the exact light curve values that typically give a precision, again, against the benchmark n-body integration, a precision which is much better than the typical observatory's uncertainty. So as actually Sam said before, studying the dynamics in an analytic way gives you a good insight into the parameters that govern the problem. What an n-body integration can't really give you. So what I'm showing you here is an illustration of a two-planet system near the 3-2 mean motion resonance in blue and orange respectively, and you can see that whenever there's a conjunction, there's another black circle. You can see that the longitude of conjunction is circulating in the retrograde sense, and the time that it takes for the longitude of conjunction to complete a full period, a full revolution, is called the super period, which also dictates the main mode of the TTV, of the transit timing variation. What we found while developing this tool is that if we have a chain of 3 planets, so we have an inner pair which has a super period Pj and an outer pair that has a super period Pk, if those super periods are close to each other, then you can't just naively sum up the TTVs of the pairwise interactions, but you also need to take into account the simultaneous interaction of all 3 planets, and we call this effect the super mean motion resonance. And I think it's a nice example of how analytic calculations can give you insights that you can't get from a full n-body integration alone. We found that for a few Kepler systems, this could be detectable in the TTV of order of a few decades. I'm showing you now one result of fitting Kepler's data using AnalyticLC. It's a system of 3 planets whose orbits are well within the orbit of Mercury, as seen in that diagram on the right-hand side. And the ratios between the orbital periods imply that there are second-order resonances involved in the system that might generate TTVs. We used the differential evolution MCMC to fit for the Kepler data, and you can see the best fitting models in orange on top of the Kepler data in blue on the 3 panels, so 3 planets and 3 transit signals folded on top of each other, and the model nicely fits the data, as you can also see in the residuals, which are shown in the bottom panels, and the residuals nicely surround the 0 line. When we get the best fitting parameter values, we also perform a full n-body integration to compare the results of AnalyticLC to validate the analytic calculation. And what you see here is the TTV of the 3 planets. It's kind of hard to see, but there are circles for the n-body TTVs and X's for the analytic calculation. And they nicely match, and I think it can also be seen from this plot that we can detect really small TTVs of order of a few minutes. The scale here is seconds, actually, so detect small TTVs that can't be discovered when using individual timing. And again, the model error is significantly smaller than the Kepler data uncertainty. Here's an overview of all of the systems we've been fitting their data using AnalyticLC for 2 and 3 transiting planet systems and 4 transiting planet systems and more. So each row here corresponds to a planetary system where the horizontal axis is the orbital period. We have the sizes and the densities of the planets represented by the actual size and the color on the plot. And we got a nice agreement of our masses with literature masses that also give us confidence about new discovered masses. So the systems with the bold and underlined text have at least 1 planet without any previous literature. What you see on the right-hand side is kind of a summary of all of the masses that we discovered. So in panel A, what you can see is that our fractional mass error is typically smaller than the former literature value, and we attribute that to the usage of the entire light curve and not only to the transit times. And you can also see in panel B that the TTV's magnitudes discovered in this work are typically smaller than the TTV magnitudes discovered just by transit analysis. Another aspect that we've been studying is impact parameter variations. So again, we're modeling the 3-dimensional dynamics, and impact parameter variations are expressions of orbital precession. So if you, for example, focus on panel B here, you see that there's a significant difference between the beginning of the Kepler data, the first 8 transit events, which are shown in blue arrow bars, and the last 8 transit events, which are shown in orange arrow bars. And AnalyticLC nicely captures these variations. The model is the solid line, the solid blue and the solid orange line. And impact parameter variations, as I said, are related to the 3-dimensional precession of the orbit. So they can be explained either by mutual inclination among the transiting planets in the system, or by other hidden non-transiting companions that apply torque on the transiting planets and generate these TBVs. So I'll wrap up. So AnalyticLC is an analytic method that was developed in order to model light curves and enable fast interpretation of light curves, but it can also model radial velocity and astrometry. And it's available in MATLAB and Python. Actually, the code was developed in MATLAB. The core code is in MATLAB, and there's a Python wrapper constructed and written by Lisa Beckman from Göttingen, so it's available also for Python users. And it takes into account the 3-dimensional orbital evolution. And during the development of this tool, we discovered a new TTV phenomenon that was unrecognized before. We called it the super mean motion resonance. And we applied this tool to the Kepler data, got many new masses, some of them without any previous results. previous literature. We detected more than 100 planets in the Kepler data with that display significant impact parameter variations, which can be related to forces out of the plane. And for future prospects, this tool can be used to model multiple data sets together, including RV, astrometry. And again, the strength of the analytic approach is that it's fast when you have a data of a long time span, which is of increasing importance as I see it. We can study the TTVs arising from non-transiting planets using this tool. And lastly, just having this catalog of impact parameter variations can be used for statistical understanding of planetary systems as a collective and not just as individual systems. And that's it, I'm done, and I'll be happy to answer any questions. Thank you.
Thank you, Yair. Let's give a hand to Yair. Great job.